Afternoon, everyone. I'm glad you could join us here. I woke up this morning in my bed in Virginia, and I'm here this afternoon to talk to you, which means that I managed to cross 3 time zones, an entire continent, and no one in my party died of dysentery. However, I did manage to pick up a bit of a cold, so if I sound congested, I apologize. My name is Eric Brownwine. I'm with the AWS security team. And today we're going to talk a bit about how AWS thinks about and manages security at scale. And before we dive into that, a little story, a history lesson. This is a German Enigma machine from World War II. Years ago, when I worked for the government, I had the opportunity to go up to the National Cryptologic Museum up at the NSA. And if you ever have the chance to do it, I highly recommend it. It was an awesome trip. They have the Enigma, they have the bomb, they have all sorts of incredible hardware there. And one of the cool things about this Enigma machine is that it's not behind glass. You can go up and actually spin the rotors and type on it. And so I have encrypted my name using this Enigma machine. It's awesome. You should do it. So I did a whole bunch of reading and learning about these machines. And the actual story is very complicated, as all actual history is. But if you look at the top of the machine, there's these 4 rotors there. This is a Kriegsmarine, a naval Enigma machine. And one of the mistakes that the Germans made with their crypto is that the Army, which was using a 3-rotor machine, had a settings. This is effectively how you input part of the key for the Enigma machine. They had a 3-rotor code for the day. Well, the Kriegsmarine code was the 3-rotor code plus a rotor, which meant that if you could crack the day's 3-rotor code, you could then use that to seed the cracking of the 4-rotor code, rather than having to crack the 4-rotor code independently. And so this was state-of-the-art cryptography in 1945. Fast forward 45 years. And Microsoft introduced LAN Manager 2.0, and I'm not throwing rocks here. This was the era when floppy disks were how you move data around. There were a lot of constraints on the design of the system, but this is the system they built. And you could have passwords that were up to 14 characters long. There were 95 possible valid characters for each of those spots. And so they would take this thing and they would hash it. And you would get a password hash out of it. And so since there are 95 possible valid characters for each spot, 95 to the 14 is a very large number, about 10 to the 27. So if you were to brute force the password to exhaustively search that space, you would have to do 5 times 10 to the 27 hashes, which is a large number. This isn't what they actually did, though. They took your good, strong password, and they chopped it up into 2 7-character strings. And they would then hash each of those independently. Well, a 7-character password, 95 possible characters, 95 to the 7th, but there's 2 of them, so it's times 2. That nets you a very large number as well. That's a large number by any standards, but it's 10 to the negative 13 times as hard. It basically eviscerates the crypto of this. And the reason I'm bringing this up, the reason this made me think, is this is effectively the mistake that the Germans made with the Kriegsmarine Enigmas 45 years earlier. And so that got me to thinking about, how do you kill problems dead? How do you solve them so they don't recur, so that they don't come back, and so that you're not constantly spending some of your bandwidth fighting them? And I wish that I had a general solution for you. I probably wouldn't be standing on this stage if I did. I'd probably be off on my island with my jet. But given that I'm here, I have at least a partial solution. So let's look at a security puzzle. You've got a bunch of engineers. That holds true of just about everyone. There's a collaboration tool that they all love using. It makes them way, way more productive. One of your pen testers comes to you and says, I have found a terrible XSS in this collaboration tool. It's terrible. So what do you do? We should turn this tool off, right? Pull the plug. Figure out how to get it patched. Okay, but then one of your engineers comes to you and says, if you pull the plug on this thing, then our productivity is going to go to 0, and we have the most important launch in the company's history coming up. It's due in 2 weeks, and without this tool, there's no way we're going to make the deadline. So you go back to the pen tester, and you're like, really? And your pen tester says, I'm pretty sure my cat could exploit this. And Like, I'm going to keep adding constraints here back and forth to get this very finely balanced problem. The risks here are very high. The risks here are very high. What do you do? How do you move forward for the business? And so at Amazon, we talk a lot about making high-velocity, high-quality decisions. And the way we do that is we escalate. Ask anyone that has worked for the AWS security team what the most frequent word to come out of my mouth is, and it's escalate. We get the right leaders involved so that we make high-quality decisions rapidly and we keep moving forward. So Andy Jassy, I'm not going to escalate to Jeff, so Andy Jassy is where I go. Well, what's Andy going to do? Andy is immediately, like right there on his BlackBerry, going to forward it to Steve and say, Steve, what do you think? For those of you that don't know, Steve is my boss. He sits in the office next door to mine, and he's going to say, Eric, what should we do with this? Now, in my defense, I've only boomeranged like this once. Like, I do learn. But if you're in security, you're going to have to form an opinion here. You're going to have a recommended path forward. You're going to have to take a stand of some kind, some recommended path forward that you can justify. So I stole this from my deck last year, and I continue to believe in this definition. I made it up myself. I didn't draw it from anywhere. I welcome it if you would like to throw rocks at it. But for me, it captures what we're trying to accomplish as a security team. We want to maximize the delivered customer value. You've got to do things. That new AppSec process that you put in place, the draconian process that makes sure nothing ever gets pushed to production that isn't perfect, that's going to grind your velocity to zero. But if you don't move that quickly, if you don't go that thoroughly, if you don't dig that deep, then what are you pushing into production that you're going to regret? How do you manage this risk? And you've got to do it over time. Whatever you do has to be sustainable. You're here for the long term. You're here to delight customers for a long time to come. And so really, it boils down to security being a balancing act. You've got the risk on one side, and every security organization spots this risk. That's easy. But if you don't have something to balance that risk, the only reason that Amazon is connected to the internet is so we can delight customers. Do you know how much easier my job would be if we could disconnect the internet? Do you know how useless the company would be if we disconnected internet? We would not be delighting our customers at all. And so if you don't have the customer value counterbalancing the business risk, you don't have a reasoned discussion. You have Chicken Little with the sky falling. And so the art and science of security is balancing these two. So I promised you shades of gray cryptically in the title, and here they are. There's this spectrum. And that collaboration example is a contrived example, that flawed tool that the cat can exploit. It's kind of like an even more geeky Kobayashi Maru. It's a no-win situation. And so whatever you come up with, if I'm asking you this question, this is the kind of question you ask in a job interview. It's not the kind of thing that actually appears in the real world. Whatever you try to do to solve this problem, I'm going to throw another constraint on there to keep it balanced in the middle. That's not the way things work in the real world. So what are we going to do? How are we going to strike this balance? Well, not literally me, but humans. This is how we solve this problem. And it's a very non-traditional answer for problems at Amazon, is humans. We're all about automation. We're all about scale. But we found this class of problems that requires human judgment. Now, the problem is that if we start cloning me, first of all, cloning doesn't work. In all my life, I've only managed to clone myself once. He's 7 years old. So if that's our plan, it's going to take way too long. We're screwed. But second of all, this is many of my coworkers' personal definitions of hell, is a whole lot of Erics running around. And this is eventually going to fail. Like, there's no way we can hire enough trained, talented, high judgment security people in order to address all of the security problems that are going to come up. And so I'm not actually proposing that we clone me personally, but I can go do a bunch of math, and I can model out the odds that a cosmic ray is going to flip a bit in a DIMM and cause a random failure. I can go do the math and figure out if 2 hard drives are going to fail within some exposure window. I can't do the math to figure out if some other researcher outside the company is going to make some creative, intuitive leap that one of my pen testers has made. I don't know how to do that math. I don't know how to predict in any quantitative fashion whether they're going to make it or not. Or worse, whether or not some nation-state actor outside the company, and for what it's worth, all nation-state actors are outside the company, has already made that leap and hasn't told anyone about it. And so here is a deeply quantitative chart. AWS is growing rapidly. The security team is also growing. It's also growing exponentially, but it's growing with a smaller growth constant on a smaller base. And this is intentional. At Amazon, we talk about keeping the bar high. We want to make sure we're hiring the right people. We don't want to lower the bar in exchange for additional growth, because that actually slows you down. And we're worried about culture as well. And we want to make sure that the team works cohesively together. And I'm not talking about a lack of diversity here. We welcome diverse perspectives. I love it when people think differently and bring different life experiences. But you want to make sure that as the team grows, they gel and they work together and they work as a team. And that limits how quickly you can grow any unit of humans. And so we've got this gap here, and this gap is going to continue to grow. Cloning isn't the answer. Hiring en masse isn't the answer. So our plan to scale via humans is doomed. So what do we add to the humans? How do we make this a more complete answer? Well, we take the shades of gray, and you're about to see some bad Photoshop or PowerPoint animations. And when you zoom out, you have no idea how many CPU cycles that just consumed. You can see that the ends of the spectrum aren't gray. There's a white end and a black end. And that's huge. That means that there are things that are clearly okay or clearly not okay. And we don't need human judgment for those. The more that we can push out of the shades of gray, the more that we can push the edges of that spectrum, the less we're going to burden our human judgment, which is, we've got some amount of bandwidth, we've got some rate of decision making that our humans can make, and you want to watch that resource carefully. So our job is clear. We need to drive everything out of the middle and to one of those two edges. But then there's that Kobayashi-Maru problem. How do we do that with a problem that's so finely balanced there in the middle? So let's talk about patching. Show of hands, who loves patching? Exactly. At Amazon, at AWS, we have patching SLAs. There's a number of compliance regimes that mandate patching SLAs. These are our patching SLAs. But when you dig into them a little bit, in particular, that critical, if we have a critical patch, then it's all hands on deck. We gather together a team of our best engineers, and we do absolutely everything we can to deploy that patch as quickly as we can safely deploy that patch. And this is hard to do. There have been times where we've gotten patches from vendors that had flaws in them. There's been a bunch of notable examples recently. And so safety is paramount here. You want to make sure that the cure isn't worse than the disease. And so this SLA, we'll do everything in our power to hit it, but we're not going to wait for 14 days. Like the moment we learn that there's a critical issue, we scramble the helicopters, we get everyone involved, and we drive as fast as we can safely drive. And we also rescore vulnerabilities. Zen has the Zen security advisories. And if you look through the back catalog of Zen security advisories, there have been a couple that are rated as importance or moderates. And one of the mitigations is don't allow untrusted guests to run on the platform. That's EC2. And so for us, we took something that was an important from the vendor and we rescored it as critical and we treat it as such. And so we're not going to automate these. They happen infrequently. We go to great lengths to make sure they don't happen, to make sure that we have defense in depth, to make sure that we're not one security control deep. And so we're not talking about criticals in the rest of the talk. And there are enough patch sets that come out that have an important in them. And we're going to automate this to the extent that we can. And we're not going to build the automation 3 times. We're going to build the automation once, because the primary virtue of the programmer is laziness. And so effectively, we're talking about a 30-day clock. That's what we're working to here. So hypothetically, you join a security team. It's a small, scrappy security team. They're pretty busy. They're responsible for a moderately large fleet. They own patching for their organization. They're metrics driven, and they show you this graph. It's pretty awesome, right? Like you're doing well. If you crank the y-axis, though, and I don't like this graph because it doesn't really represent the growth of the fleet, but when you crank the y-axis, you can see that these two lines don't actually correspond. There's a gap between them. And so it's useful to be able to see what they're not the same, but I don't like this as a visualization. This isn't something that I would put on a dashboard. Well, we're a security team. I really don't care how many boxes are patched. I don't want to dislocate my shoulder patting myself on the back. I care about how many boxes are not patched within SLA. That's the gap. That's the thing that we as a security team need to remediate. We want to drive that red line to 0, right? Well, so this is a better graph. But as graphs go, this is still pretty terrible. Like, there's that red thing right there at the bottom. Can you tell anything at all about it? And so we zero in. The y-axis is still zero-based. So this isn't lying like that one chart I didn't like. But you can see there's a little bit of movement here. The line is not completely flat, so something is happening. But this chart doesn't really give you anything actionable. If I hand this chart to an engineer, what are they going to do with it? They're going to stare at it blankly and say, I don't know. And so I like this graph. This is the kind of graph that belongs on a dashboard. I want that red line to go to 0, but this graph isn't actionable. I can't hand this to an engineer and have them quickly make judgments about what should be happening here. This is going to tax my human judgment bandwidth. And so we crank the y-axis again. And so it's not zero-based. It's starting to get into unsavory visualization territory. But this graph is interesting. The overall trend is down. That's good. These are boxes that are not patched within SLA, so down is the right direction. But it's not going down very fast. I mean, it's gone down about 100, and the x-axis here is about 120 days. So a box a day, like that's not very good. But there's massive movement on top of that general downward trend. And there's some big movements too. Some really big movements here, a couple hundred boxes at a time sometimes. Like, what do I, as a security professional, need to do about these jumps? What is this graph asking me to do? I don't know. Like, how do we investigate this? Do we set a threshold? Do we pick some n and say, as an engineer on call, you need to look at everything that's more than n machines different from an hour ago or a day ago? Like, how do we set n? What if something sneaks past? And if I set a bunch of engineers on this task, and there's all of these movements in this graph, and that pager is going off all the time, that alarm is going off constantly, are they actually going to do the job? And I did a bunch of reading on the topic, and there's a whole bunch of research papers that have been written, mostly about emergency rooms and hospitals. And the research is not positive. Humans are not good at this. And what they found is that if there's a low rate of false alarms, and if the alarms are highly actionable, then humans continue to respond. This is why when you dial 911, or whatever your local incantation is, the police and the EMS and the fire engine actually shows up at your house. The rate of false alarms is low, the alarms are highly actionable. But then you move to a hospital setting, and they have all of these machines, and every time any parameter goes out of spec, an alarm goes off. There's a beep, there's a buzzer. And they called it alarm deafness. And these very dedicated doctors and nurses have these tragic accidents because there's so many alarms going off that they become deaf to them, they become inured to them. And so when life and death is literally on the line, human beings do a bad job of keeping up with the alarms, what chance does our scrappy security team have? I mean, what's a couple of unpatched boxes compared to a human life? So we've got to be really careful here about interrupting our humans. So look at this. Think how many times your pager would have gone off if we set n too small here for the threshold. Think about how many fleet movements would have gone past you without an alert if you set n too high. And so there's not a lot I can do with this graph, especially when you take alarm deafness. We need another path forward. And so we're right here in the middle. This graph is middle gray. It's not telling me to go this way or that way. We're measuring the output goal. We're measuring the result that we want to see, but we're not seeing a lot that's actionable. So let's do what I talked about earlier. Let's try and drive some of this work out. So why aren't boxes patched? How many of you have legacy software? Just about every hand went up. I have a feeling that the people that didn't raise their hands either, one, don't like audience participation questions, or two, have not yet discovered their legacy software. We have some RHEL 5 boxes. We need to support them because we need to be able to build and test software that runs on RHEL 5 for various legacy reasons that I'm sure you could recite by memory. We have to have these boxes. RHEL 5 was released in 2007. In 2017, Red Hat finally pulled the plug. They said no more. And so these boxes are unpatchable. We know that they have vulnerabilities. We know that the vendor is not going to come out with patches. You can see we don't have very many of them. And we know they're not getting patched. And so we've put them on an isolated network. We watch the heck out of them. They're not allowed to talk to anyone except the people that we expect to be talking to them. And we mitigate the risk that way. But these boxes are never going to be patched. We also have, you may be aware, Amazon has data centers. Data centers are technically buildings, but they're really large machines. They've got fans and chillers and water pumps and all of this complicated machinery that's moving fluids, whether it's air or water or whatever, around in large volumes. And this needs to be done carefully and in a coordinated fashion. So we have building management systems and EPMS, electrical power management systems. And the vendors that produce these things, they've been in business for decades. And they've produced these controllers for decades. And recently, these controllers have become internet connected, or internet connectable, I guess. And to the vendor, this is any standard industrial controller. In the absence of maintenance or new features, these things have a service life of 20 or 30 years. But to us, it's a general purpose operating system on a network, and it has to be patched. And so you roll out the OS vendor supplied patches, and that often breaks the industrial control software. And we need the pumps to keep running, we need the chillers to keep running, and we want the boxes to be patched. And rock in a hard place here. And so again, we have isolated these things. They're on their own firewalled network. Every packet that comes out of these boxes is scrutinized. Very few things can talk into these boxes. They can't be patched. We actually have the patches in many cases. Just installing the patches breaks the reason the box exists. And so, again, we've mitigated the risk, but we know that they're not going to get patched. And so we take it as a deeply held belief that we want to know about these things. Our inventory system is complete. If it has an IP address, we want to know what it is, and we want to know what its patch state is, even if we know that that patch state is going to be read. And so we've got them. We know they're not going to be patched. We've mitigated the risk another way. And so we've got a couple of things that we expect. And so when a BMS server shows up on the report as unpatched, my engineers don't need to do anything. When a RHEL 5 box shows up unpatched, my engineers don't need to do anything, assuming it's on the correct network with the right ACLs, which we check. But again, we've defined a category of systems where when the violation occurs, when the unpatched state occurs, we don't need human judgment to respond. Now, in these two examples, the volumes are pretty low. We were looking at about 10,000 boxes that were out of SLA, and I've got, what was it, like 240 that I've just identified? But you just keep taking slices away. And we know that as long as these systems are in the state, we never need to pay attention to them again. And so we've shrunk the ambiguity. So let's pause here for a moment. Entitlement is a common English word. I'm not talking about millennials and what they deserve and all of that. There's a specific technical definition of it that I've only ever heard used at Amazon. I don't know if it's used outside the company. I don't know if Charlie Bell made it up himself, but I found it to be incredibly useful. And so to talk about entitlement, let's look at an example. You've got the operating system, And you need to get it onto the disks. The arrow is backwards. My PowerPoint skills are not as good as I want them to be. So your leadership comes to you, and they say, it takes too long to build boxes. Like, it's too slow. It takes 50 minutes to build boxes. You need to cut that in half. You're gonna 50% reduction in the amount of time it takes to build a box. So let's do the entitlement exercise. The power on self-test takes 2 minutes. This is when you apply power to the box and it checks a bunch of stuff out. The operating system load itself, well, the operating system install is about 30 gigabytes. Your disks can absorb data at about 100 megabytes a second. The network isn't a constraint in this case. The math works out to about 5 minutes. So the actual operating system load, assuming you just do a single pass write across the disk, takes about 5 minutes. We flash the firmware on every box before it goes out into the fleet. It takes about 4 minutes to write out the firmware. The problem is that while you're writing the firmware out, you have to reboot twice, so that each reboot takes about 6 minutes. And then we have learned through painful experience that the last thing you do before you hand a box over is you reboot it one more time, because I would rather it reboot and die during the build step than that it reboot at some point in the distant future when there's a power failure or an issue. And our service owners learn that all of the boxes built with this image no longer reboot. And so that's going to add another post, full metal reboot. And so our entitlement here is 31 minutes. This is not engineering work. This is paperwork. This is literally sitting down with someone that knows the details of this system for 15 minutes, longer or less than the time it takes to load the operating system, and saying, like, what are the steps and how long do they take? And we're talking about laws of physics constraints. The odds are that your OS installation process doesn't keep the disk saturated at 100 megabytes a second. Odds are it's way less efficient. This is your entitlement, though. If you're perfect and you don't change any of the constraints on the system, this is as fast as you can go. And if you look, these two numbers don't agree. Your leadership has taken this 50-minute number and they've made up a goal, but the entitlement tells you that you can't get there. And so in the old world, 50 minutes, waste. Like, honestly, my leadership does not believe that everything that I do is a waste, but in the absence of data, like, what decision are you going to make? And you know, if you've ever negotiated buying a house or a car or something, I don't know, you want it to be 0, it's 50 right now, how about 25? And so, like, that's a scientific way to pick a goal. Well, in the post-entitlement world, our total time is 50 minutes, our entitlement is 31, our waste is 19 minutes. All right, let's meet in the middle again. Let's shave 10 minutes off. And it turns out that shaving off 10 minutes is an aggressive goal. Like, that's actually the meet in the middle goal, not 25 minutes. And so this concept of entitlement I've found to be really useful in all sorts of arenas, including security. And so we've identified a couple classes of hosts that we don't expect to ever get patched. I'm not entitled to drive that red line to 0. It will never get there. If my goal is to drive that red line to 0, I'm going to fail, because we know that there are reasons that I can't make it there. And so if I take that as a goal, I'm always going to have this nagging voice in the back of my head telling me that I'm going to fail, that I'm doomed, that this is not going to succeed. And so you've got to be really, really careful about what you pick your goals to be. This purple line here, I can probably drive that to 0. And I'm going to drive it to 0, 1, by patching hosts, and 2, by identifying other boxes that I'm not entitled to patch. And again, if there's an unpatched host, there have to be other mitigating controls in place. It's not okay to just say, well, it's hard to patch, I'm going to leave it on the network. But I'm going to identify these classes of things, and I'm going to shift them out into the white part of the spectrum. We need to carefully define goals. And so, motherhood and apple pie, right? Drive the number of out of SLA hosts to 0 and keep it there. A lot of people leave off the and keep it there. And one of the things that I've learned is that people will drive the goal you give them. And so Tuesday is like, that was the watershed date. The fleet hit 0. And we mark the goal as green, and then everyone goes back to their day jobs, and you look again in 6 months, and you don't like what you see. And keep it there. But this is still, because of the entitlement discussion, a terrible goal. You're not going to get people behind this goal. Everyone's going to have a reason why this goal is impossible. It's going to be hard to align the organization. And so This is a much better goal. And actually, in AWS, a lot of our goals are even longer than this. They're very carefully defined because you want to have control over whether you meet the goal or not. You want the goal to be achievable, and you want to be able to hold people accountable to the goal. And so there's do not have valid approved exceptions language in there. What's an exception? Well, there's that thing you're deprecating in 2 weeks, and it's going to go out of SLA in 10 days. Is it really worth it to spend the time patching it? Or there's that fleet where you installed the patch and your throughput dropped to 50% of what it used to be. Like maybe you get a 2-week extension on the patch SLA so you can root cause that performance regression so you can actually deliver to our customers. Because if we drop our performance to half, the fleet is going to do what it's actually supposed to do. Like there's all of these complex trade-offs. But because you pedantically define the goal, anything that doesn't have a valid exception, whether it's rel 5 or BMS or that thing that's being turned off on Tuesday, then you can drive it. And so we want to drive this purple line to 0. We want to drive it to 0 by actually patching and by finding new things to exclude. And so the line is a bit flatter there in the middle. That was that big humped BMS fleet movement. And so we've gotten that, like, you know, the noise on this line has gone down a little, but there's still a whole lot of jumps in this graph. There's way more than I can have a human dig into here. There's still the danger of alarm deafness. So let's switch gears. What do we think is patched? Like, where do we think that we're done? Well, corporate networking team. These are vertically integrated networking switches. They're the kind of things where there's a single firmware image and a single text file that defines the state of the device. And our corporate networking team is all over this. Like they've got tools for deploying these things and managing these things and updating these things. And so you filter them out, you isolate them just to that one fleet on a graph, and you expect it to be 0 because they're on top of things. But this is what you find. And that pattern is awesome, that little heartbeat pattern. And you dig in. This is actionable. Like a human being, you look at this graph, you're like, something ain't right here. And you dig in. It turns out we had 2 tools, one of which kept putting a device into service. Then our patch inventory would run. Then another tool would run, find the box that was out of date, and pull it from service. And so we had these 2 processes in a tug of war. And we fixed it. And you can see the graph went flat at the end. Life is good. Or this. This is the graph. This is a graph that I love. I can pull any engineer off the street, and I can show them this graph. And I don't have to tell them anything else. There doesn't have to be a single bit of text on this graph. And they look at it, and they're like, that's bad. I need to do, like, something is... The amount of human judgment that this graph is consuming is epsilon. This is an incredibly actionable graph. Now, it turns out when you dig in that this was a bunch of S3 web servers in a region that was not yet released to customers. And so we had a gap in our tooling. We had deployed the boxes. We were monitoring the boxes for patches, but the automated patching hadn't been deployed to that region yet. And so we fixed the underlying root cause. We patched all of the boxes that were out of SLA. But this graph is the poster child for the kind of graph that you want to be able to have. This is incredibly actionable. This puts minimal cognitive load on your humans. And so if this graph deviates from 0, we have a problem. And we know we need to engage. It's super clear. And so now, if we look at the shades of gray, we've identified a couple of things that if they occur, they're clearly bad. If we see something here, we know we need to respond. Immediately, you engage. And so if this happens often enough, then you automate the response. And again, you pull your humans out of it entirely. If it doesn't happen often enough, at least now you know, without any cognitive load, without any alarm deafness, that this is something that we need to do well. And this, again, it helps you align the organization. Saying we have this big amorphous Gordian knot that we need to untangle is really hard to get people motivated. Saying, surely this very narrowly defined thing that we all agree to, that should be perfect, right? And everyone will go, yeah. And then you get the data. And if it's not perfect, people jump. And so when you look at a graph, you have to ask, what do you want from me? And in the left graph there, I don't know. Like, it's an interesting graph. There's a ton of knowledge to be gained from that graph. But as a responder, as someone that's trying to deliver security, this is the kind of thing that belongs in a dashboard. This is the kind of thing that you want to look at occasionally. But I can't jump. Whereas that right graph, no words on it. I don't know what's going on there, but I know that I need to dig in here. And 100% of the time that I see that graph, I'm going to dig in. And so, really, it all boils down to, is this number 0? It's such a simple question to answer. The human visual cortex is incredibly good at answering the question, is there something there? And if the number is not 0, you jump. I'm not even asking you to do math like you are when you say, does the number of boxes patched within SLA match the number of boxes? Like, it's simple addition and subtraction, but even that places more cognitive load on the person looking at the graph. Whereas, is this number 0 is incredibly easy. And so if the expected answer to your question is not 0, adjust the question. Find a question whose answer is expected to be 0. Keep doing this until you get that question. And then every time that answer isn't 0, you jump. And this seems like such a trivial change. And this is something that we stumbled on after looking at untold numbers of graphs and monitoring untold numbers of metrics. It's a huge, huge difference in the response that you get from your engineers and in the response you get from the organization. It pains me that the punchline of this talk is literally nothing. But I have come to love the number 0. Like, this is an incredibly powerful technique for focusing the attention of your humans such that the maximum amount of their bandwidth is spent on the Kobayashi-Maru style problems where human judgment is needed. And so this is where the enigma lesson comes in. You don't want to send a bunch of humans in to solve a problem because they will. Like, humans, we're creative, we're intelligent, we go and we make things better, but we make it like 90% better. Humans aren't a mechanism. And so then you turn your back on it because there's the next big problem. And that one's doing okay right now. I mean, heck, it's like practically solved. And then you go to the next thing and you're focusing your attention over here and that one festers and it turns evil again. And pretty soon, the number of balls that you're juggling, and I'm a very bad juggler, so this is a bad way for me to spend my time, grows huge and it grows untenable. Whereas if you keep taking slices of the problem off and asking questions whose expected answer is 0, and then every time they deviate from 0 you jump, you've solved those problems, you've put them to bed. And so saying, let's patch everything, like, yeah, we're going to take that hill. Everyone's really excited for about 15 minutes. I couldn't even say a week, like I've never seen that happen. But saying this critical fleet, this one here that we all agree is really important, let's keep that patched. And that's going to drive the development of tools, and that's going to allow you to pick the next fleet, and the next fleet, and the next fleet after that. And so we're back to the shades of gray, and we've got the ball of ambiguity in the middle, and we're pulling things out that we know are okay, that we know our engineers don't need to respond to. And we're pulling things out that we know our engineers need to respond to immediately. And this is shrinking down that ball of ambiguity. And this is a process that you can drive relentlessly. And you're never going to shrink that ambiguity to 0. This is what security people call job security. But as you pull things out of that ball, they're done. And so there's no cognitive load on your engineers. You're taking off these little slices, and that process compounds. And you can keep driving this as long as you have the bandwidth. In the United States, and while researching this talk, it turns out in Japan as well, I don't know about the rest of the world, we have a game called whack-a-mole. And so there's these 5 holes, and there's these mechanical moles that pop up, and you've got this one padded mallet, and it's your job to whack these moles on the head. And I actually had my spelling corrected. If you're using whack-a-mole, the trademark name, there is no K in it. It's your job to whack these moles on their heads to make them sink down, and they keep coming faster and faster, and there's 5 holes and only 1 mallet, and eventually you're bound to lose. And so what we're doing here is we're methodically riveting caps over these holes. And in some idealized security world, maybe you get to ignore 4 of the holes while you focus on one of them. I've never lived in that world. I'm not recommending that you focus 100% of your bandwidth on one problem. But if you can focus a fraction of your bandwidth on one problem, and you're doing enough with the other 4 holes, you're staying afloat, you're getting ahead a little bit, but you've got enough of your bandwidth reserved that you can start solving one problem completely. Eventually that problem is solved. And then you move on to the next hole, and the next hole, and the next hole. And the whack-a-mole creators would consider this cheating, but in the security world, I'm okay with it. And eventually, there are no more holes left, and no more moles can pop up. Now, this isn't the world we live in. We live in a world of heartbleed and eternal blue, and who knows what the next thing is going to be. There's always going to be another hole forming on the top of this board. It's an imperfect analogy. But as long as you can dedicate enough of your bandwidth to solving problems permanently, such that you solve them faster than you create new problems, you can win this game. You can at least stay afloat. A lot of people ask me when I talk about this how we manage all those zeros. How many zeros should I have? And this visualization here, I did not come up with this myself. I stole this from Edward Tufte. The visual display of quantitative information is excellent. You should read it. He's a little bit rabid about some of his points, but there's a lot of insight to be gained in that book. And he talks about small multiples. And the idea is that you can shrink these graphs down until they're tiny, and they don't lose any of their expressive power. I fit 6 graphs on this one slide, and you can read all 6 of them. They still tell you everything that they were telling you earlier. They haven't lost any of their information content, but they're all on here. I could probably have fit twice as many on here. And so you can have a dashboard that has a ton of zeros on them. And those first 2 graphs, they're still just as actionable as they were when they were full screen. In fact, one of the hacks that I like is you can add all of your zeros together. Because it doesn't matter how many zeros you add together, the answer is still expected to be 0. And so you can have one graph, and the graph can be titled Things That Should Never Happen. Now, you have to have discipline here. If that graph falls into disrepair and that line is squiggling all over the place, if it's like the upper right chart here, you've lost it. It's no longer valuable to you. It's no longer zero cognitive load. But as long as you're disciplined about it, as long as the things that should never happen, anytime that graph deviates from 0, you jump on it with 2 feet. You drill down on that graph. You've got the one master 0 at the top, you drill in, you've got all of the little graphs beneath it, you figure out which one or ones of them, if you're having a particularly bad day, have deviated from 0. Your engineers know exactly what they need to do, and they dive in. And so it's okay to have a ton of zeros. You keep nibbling away at the gray. You keep removing distractions from your humans so they can focus on the things that they need to focus on. And we do this constantly. This has become part of our background. We have all of these tools that check things. And so, for example, I get all of these emails from these automated tools. And there's this long, complicated email about how many API calls we made and how many things we checked and which accounts we validated. And the email scrolls on for pages. But in the subject of the email is the number of unexpected violations. And so I can pull my phone out and I can look in that folder, 0, 0, 0, 0, not 0. And I know exactly where I need to dive in. It's wonderful. And you just keep accumulating these things. The zeros themselves are not expensive to maintain. They are at least cheaper to maintain than the problems they replaced. And so how do we get to 0? You want to make these zeros. You've got to untangle that Gordian knot in some way. And so let's pick a fleet. You expect it to be 0. You expect it to be 100% patched or whatever the thing is that you're measuring. And it turns out that it's not. It turns out when you dig in that one of the deployment tools is misconfiguring the hosts. And this is constantly happening. Deployments are going out to the fleet all of the time. And so this deployment tool is basically a little factory. And it's a little factory, another amazing PowerPoint animation here. It's a little factory. You have no idea how hard the timing on this was to get right. It was such a waste of time. It's a little factory that makes presents for you and the service team to clean up. So what do we do here? How do we attack this problem? Do we go FIFO, first in, first out? Find the oldest misconfigured host, fix it, and start working it that way? Or do we go LIFO, find the most recently misconfigured host, and work it the other way? Now, which end of the snake do you eat first? And to the extent possible, I always choose to start with the factory. I always choose to start with the source of the problem. And as a security professional, what you really want to do is you want to reduce risk. And the thing that reduces risk the fastest is fixing these presents, repairing these hosts, getting them back into the green state. The problem is that you're basically running up an escalator the wrong direction. You can totally do it. I haven't done it since I was like 10. But doing it professionally seems like a really bad idea. Whereas if you can spend as much of your bandwidth as you can afford, I don't know what's in these presents. I don't know what the risk is that they pose to your business. You're going to have to make some reasoned human judgments there. But to the extent possible, if you spend your bandwidth fixing the factory, you've now split the problem into two and immediately given yourself a zero. The number of hosts deployed after some watershed date that are misconfigured. That should be zero. You fixed the factory. And so now you can add that to your list of zeros. You can add that to your dashboard. And now you can ignore the factory. Because you know that if anything goes wrong with the factory, your zero won't be zero. You need to respond. And now you can wholeheartedly focus on the set of hosts that are left. And I found that there's a morale benefit here as well. The running up an escalator state is a bad place for an engineering team to be. Like, you're making great progress, you're doing amazing work, and the finish line keeps receding away from you. It's demoralizing, it's draining. Whereas if you know, like, we're done here. Like, there are 43 of these. There will never be another one. Let's go. Like, you know how long it's going to take you. You can do the math. And, like, you can get people behind that. And then that gives you a second zero, the number of hosts that are misconfigured, period. Yes. So I want to eat the snake in that direction. Anyway, I am ecstatic that I managed to put World War II cryptography, Star Trek, and whack-a-mole all in one talk. Entitlement is incredibly important. It was like being hit in the head with a brick when I first learned about it. It was a concept that I hadn't ever thought about. But when it was explained to me, I started finding uses for it all over the place. And I use it all the time now, in security, in performance management, in all sorts of aspects of engineering. And once you understand entitlement, it changes the way you take goals. Because you want your goals to be absolutely achievable. You want them to be ironclad things that you can positively drive. And so once you get your goals defined right, and you can honestly hold yourself to them, then you can get the entire organization aligned behind them. And for most security questions, I like making the answer zero. And sometimes it requires asking really convoluted questions. You've got to kind of do the math ahead of time so that the answer comes out zero. But if you do, you're catering to your humans. And we really do think of our humans' cognitive bandwidth as a constrained resource. And every time you look at a security ticket, an email, and anything, a graph, a chart, a report, you ask, what am I asking the reader to do? How do I want them to respond to this? How much effort is it going to take for them to respond? And if it really is a Kobayashi-Maru problem, and I happen to be with Kirk on this one, I don't think that those problems exist in the real world. If we go back to our collaboration example, if this really is the most important launch in the company's history, like, is there some other tool that we could use? If it's actually that important, like if this is a make or break for the company, maybe we do something unthinkable and we put everyone on an airplane and we put them in a room together and we collaborate like we used to in the Dark Ages. Like, every time I found one of these very finely balanced judgment problems, as you dig in, as you learn more about the problem, there are always options that appear. I don't believe in the Kobayashi-Maru. But I do think about how hard it's going to be for the people that are answering these questions to answer them. And when you compound that out over time, I'm not here to keep the cloud safe this week or this year. I'm here to keep the cloud safe for as long as we have it. And it's going to be exhausting. It's going to be tiring. And you've got to recognize that. You've got to realize that this is a marathon, and you need to make sure that you manage what you're asking your humans to do, where you're applying them, and that wherever you can, you're unloading them. There's a ton of related talks on security here. We've got a huge security track. I actually think that first one there, back, is Beetle, and that's in this building in 30 minutes. Beetle is an engaging speaker, so I recommend it. A lot of security content this week. Feel free to tackle any of us if you have any questions. And thank you very much for your time and attention.